Okay, so in the previous discussion we had stopped here. So just in case anybody wants to view that part of the discussion, they may refer to the part 1 of the video of the concentration series, concentration inequalities series. So we had stopped here basically, and we had reached the conclusion that probability that x is greater than equal to epsilon is the same as probability of y greater than equal to lambda epsilon, and this already came from the Markov inequality. So at this stage, let us move ahead. At this stage, the question is, are there any conditions on when is this inequality correct? Let's go through it one by one. In this part, it is entirely based on Markov's inequality, right? So once we have used e to the lambda x, we are ensuring that y is positive. So here already we can apply Markov's inequality, and because e to the power lambda x is positive by definition, and this condition is equivalent to x being greater than equal to epsilon, and therefore up to this stage there are no conditions, and this means this inequality is as powerful as Markov's inequality. So till here there are no conditions. Now the trouble here is that we have got MGF of x involved, and MGF is not something which is easy to calculate for any distribution, for any given distribution. But in a special case, now we insert a condition. So let me try and use some other color. Red wasn't visible, I remember. Let's use maybe blue. Now we insert the first condition, and now the condition we use is that x has been taken from a normal distribution, say 0 comma sigma square, better, not mu square, very say 0 comma sigma square. And as soon as you take this assumption that x is Gaussian, right, immediately we get MGF of x to be e to the power lambda square sigma square upon 2. This is a result which you can find out. Basically, you can use the distribution of 1 over whatever 2 pi sigma square and so on. You can write the distribution, go x, so e to the power lambda x dx, and you can integrate it from minus infinity to infinity, and this is what you will get as a result for the MGF of that distribution. It is simply e to the power lambda square sigma square upon 2. Okay, so now things change, because when you put this there, e to the power lambda square sigma square by 2, what do we have? We get probability then that x, and now for this condition is what we are writing, the probability that x is greater than or equal to epsilon is less than or equal to, we had initially MGF of x remember this result, mgf of x upon e to the power lambda epsilon. So in this case we get e to the power lambda is square sigma is square upon 2 and then minus lambda epsilon. So it is less than this, but we see that this has a lambda dependence and this is independent of lambda, right? So that simply means that for whatever value of lambda we choose on the RHS, we get a correct bound for x greater than equal to epsilon. So because it is independent of lambda, we would like to choose a lambda such that we get the tightest possible bound, the best possible bound. So we want to say that the probability that x, that is we go wrong by more than epsilon, should be very less. That is what we are aiming for. We are aiming to reduce this delta part. So we want to reduce this. So what do? We claim that this would mean that probability of x being greater than or equal to epsilon is less than or equal to, you can say, the infimum of or the minimum of overall lambda. We can choose any lambda. We take the infimum over of all lambda of e to the power lambda is square sigma is square upon 2 minus lambda epsilon. So now we need to choose a lambda such that this is minimum. And what does that mean? Exponential is a monotonic function, so basically we want to minimize the exponent, and exponent is nothing but a parabola, right? The exponent part is simply a parabola and its base is at minus b upon 2a. So sigma square upon 2 epsilon is its base. Minus b upon 2a. So the base is basically some, you can calculate it. Basically it is just this thing, and you want the value at this point. This is the minima, right? So at which lambda do we get this minima? Because this is a plot of lambda is square sigma is square by 2 minus lambda epsilon. So at which lambda do we get the minima of a parabola? And as we know, it is at minus b upon 2a. If it is in the standard form ax squared plus bx plus c, here a of course is sigma square upon 2. So if you put it, it is epsilon upon sigma square is where you get the minimum value of this parabola, and you can just put lambda star equal to this value epsilon over sigma square in here to get the minimum value. So just put lambda equals to epsilon upon sigma square. So when we put the value, what do we get? We get this exact same expression that we wrote, that probability of that we wrote for Chernoff bound, that probability that x, right, is greater than or equal to epsilon is less than or equal to exponential of, and just put lambda star equals to sigma square, and let's see what do we get. Lambda star equal epsilon upon sigma square. So this is epsilon square, right? And you get sigma to the power 4, so upon 2 sigma square minus lambda into sigma is epsilon square sigma square, and and this will be equal to exponential of, what is this? This is simply minus epsilon square upon 2 sigma square, right? And well, just to simplify it, what we had wrote earlier, it is minus epsilon square upon twice variance of x. So in this case we see this all goes through, and then finally the last stage, as always, is to just put now this is a substitution, that x you replace it by mu m star, and it is simple because then you get probability that, I mean this should be obvious now, mu m bar greater than equal to epsilon is less than or equal to exponential of minus epsilon square upon 2, and what is the variance of mu m bar? Well, that was just you will get 1 upon m square times m times variance of x, so that is variance of x upon m, so m goes in the numerator, and you get this result. And this is what we get for a one-sided inequality. You can also do the same to get mu m bar less than equal to minus epsilon thing, and you will get another similar inequality, that is exponential of minus m epsilon square upon 2 variance of x, and you can take a union bound of these two to get your final results. That gives us a factor of 2 here, and our original result just comes out from it. Okay, so now we have proved both the bounds, and we obviously know that the Chernoff bound is tighter than Chebyshev bound, but it is useful only for Gaussian or sub-Gaussian random variables. The final thing which I would like to introduce is what is sub-Gaussian random variable, because the Chernoff bound is valid even for sub-Gaussian random variables. So let us see where we actually used Gaussian thing, right? We used the Gaussian property here in the part for MGF. If we can say that some function has an MGF which is even tighter than e to the power lambda square sigma square by 2, we are through, right? For that as well, everything would go through, in fact in a tighter way. So sub-Gaussian random variable is defined the same way, that x is sub-Gaussian. Okay, so color change maybe, yeah. We define it in the same way, that x is sub-Gaussian means, and in fact we call it x is sigma sub-Gaussian if we have some lambda for which the expected value of e to the lambda x, we have some sigma such that the expected value of e to the lambda x is less than or equal to what we had MGF of Gaussian. how is this helpful? Because then our inequality was that probability of let me just I have just messed this up. Our inequality was that probability that x is greater than or equal to epsilon is less than or equal to mgf of x upon epsilon is square, I believe, or something else, I don't know, let me check. E to the power lambda epsilon, sorry, yeah, I messed it up. Yeah, right. So if we already know this for a Gaussian and we got some good bounds for it. Now if this is even less than the mgf of a Gaussian, then if the inequality holds for a Gaussian, it would hold for this as well. So the thing is that the bottom line is that even for this class of distributions for which the mgf is less than mgf of Gaussian, and what is mgf of Gaussian? Let us replace it. mgf of Gaussian is simply exponential minus lambda square sigma square upon 2. So there exists a sigma. So if you can find a sigma, right, for which we have distribution x such that its mgf is less than equal to exponential of minus lambda square sigma square by 2, and there exists some sigma for that purpose, then x is called sigma sub Gaussian. This is simply mgf of Gaussian and we want something better than that. This is mgf of x. So if we get something better than that, it is sub-Gaussian random variable and it satisfies Chernoff bounds. Interestingly, we have a nice case. So a case in point which we will be using is uniform random variable. A uniform random variable, or I think this is just a small case. Let me mention the more general thing first, right? That any bounded random variable is sub-Gaussian. And this is an interesting result because say x is bounded, right? It belongs to say a to b, right? Then it is sigma sub-Gaussian, where sigma equals to b minus a upon 2. It is sub-Gaussian. The only condition is that its expected value that should be 0. But even if the expected value is not 0, we can subtract the means from all the instances of x and center it. So I will write down else center it, right? So you can center it to this, and yeah, you can always make it a sub-Gaussian thing. So you know sigma and you know our bounds, right? That is, you can say that with this sigma it satisfies the Chernoff bound. And what was the Chernoff bound? So for any such variable, so I mentioned this before uniform random variable, because uniform random variable is also something which is bounded, minus a to a. So if this is given, we can use Chernoff bounds on this. So probability that mu m bar is greater than or equal to epsilon is less than or equal to exponential of minus m epsilon square upon 2 sigma square, and just put the sigma here to get some values. Okay, so that's it. That if you have a bounded thing, it is sub-Gaussian, and hence you can apply Chernoff bound on it. So this pretty much ends whatever I wanted to cover. Now what I will do is that I will just summarize the results, because anyway we would be needing the results more than the proofs themselves, and I hope we have went through the proofs very well. So what I will do is that I will maybe draw an enclosing box around all this. I'm just trying to fit it in. What is the exact percentage? I think 15 is the optimal thing. Okay, maybe 13 looks good. Let me see if I can draw a shape somehow. I don't think I can. Okay, let me try and draw it with hand. Oh no, that is bad. Or okay, so I do have a ruler. A minute. Oh my god, what is this thing? Okay, let us leave it. I don't know. Or maybe I have another plan. A minute. I just wanted to enclose these in a bounding box so that we can now just list down the central results that we have obtained till now. Right. Okay. So I will now be summarizing just all the results, and that's it. Now we can maybe zoom out and just let me now just summarize. Yes, so maybe this is good. Okay, so for summary, oh oops, I just habit of writing small. So just for summary, we can conclude that the fundamental thing we discussed was Markov inequality. And Markov inequality was simply that probability that x is greater than or equal to epsilon is less than or equal to expected value of x upon epsilon. And there were two conditions: x is positive random variable and epsilon is greater than 0. This was A. Then a B was that, oops, what? It wasn't working when I was drawing lines and now it suddenly starts to work. So B was that probability that x is greater than or equal to epsilon is less than or equal to the MGF, which is expected value of e to the power lambda x upon e to the power lambda epsilon. Again, I think this is, again, we had taken y equals to that and applied something, so it is, there is no constraint. The only constraint is epsilon greater than 0. X need not be a positive random variable here, because all we cared about was e to the power lambda x upon e to the power lambda epsilon, which came out of y, so it is not an issue. So these were the melting pots of all our inequalities. Then we did some proofs and we reached at two more inequalities. One was Chebyshev and Chebyshev is simply that probability that mu m bar minus mu is greater than or equal to epsilon. This thing is less than or equal to variance of x. So the larger the variance, the more the chances that we go out. So if variance is higher, we are less confident about the bounds we are putting. Variance is high, delta is high, that means 1 minus delta, that is the probability that we lie inside this range, that is low. So variance of x upon m epsilon square, I believe this was the result. And it was condition free, and then we had Chernoff. And Chernoff is simply the same thing. The probability that mu m bar minus mu is greater than or equal to epsilon is less than or equal to twice exponential minus m epsilon square upon 2 variance x. But this is valid if and only if you say sub-Gaussian or Gaussian. Gaussian is also sub-Gaussian, so expected value of e to the lambda x, which is the MGF, is less than or equal to if our MGF is less than or equal to the MGF of a Gaussian, which is exponential of lambda square sigma square by 2, right? So another oh my god, yeah. So finally, for Chebyshev, Just to conclude some properties then. One was expectation is linear, of course. Expected of x1 plus x2 is expected x1 plus expected x2. And variance of x1 plus x2 is equal to variance of x1 and plus variance of x2. x1 comma x2 independent, and variance of ax is simply a square variance of x. So these are the three results which we used, and just as a sketch of what we did for proofs, for Chernoff, for Chebyshev, we used y, or we used two substitutions, that is we replaced x with x minus expected x square and epsilon with epsilon square, and we just used Markov. We put these results into Markov, and we and then finally we used x we replaced by mu m bar, and we got a result for Chebyshev. For Chernoff, the path was slightly longer and interesting. Okay, so first of all we proved how to get from here to here, right? Here to here you use simply y equals to e to the lambda x, so that x greater than equal to epsilon is equivalent to y greater, let's see, so not y exactly, let us write it down, becomes equivalent to e to the power lambda x being greater than or equal to e to the power lambda epsilon, and this is simply our y, and use Markov. So this bunch of steps gave us this inequality. Once we got that MGF1, that it is MGF upon e to the power lambda epsilon, Chernoff is just using MGF of Gaussian is equal to exponential of lambda square sigma square, lambda square sigma square upon 2. We use this and put it there. Basically, even if it is less than that, MGF is less than exponential of lambda square sigma square 2, then also we are through. We use it, we get the Chernoff bound, which is twice. Okay, and have I missed something anywhere? I feel no. Okay, fine, it is good. So it was variance of x upon m epsilon square. It is twice exponential of minus m epsilon square upon twice variance of x. You use this and you get there, and then the final result was bounded implies sigma equals to b minus a by 2 sub-Gaussian. And that is pretty much it. That is all we did. So now, given we have a distribution and we take m samples out of it, the realized, the sample average, which is mu m bar, we now know what it will be, right? How close would it be? So we have got the concentration inequalities. I hope so. There is nothing left. Let me just check once from my notes, maybe. I think this should be it. Okay, so just for terminology, if you use this for bounded, case, that is when you use sigma equals to b minus a by 2 for a bounded random variable, mu m bar minus mu greater than equal to epsilon, and so on, and you just put sigma equals to b minus a by 2 here instead of variance, and you use, this is basically sigma square, this is also sigma square. So when you do this, it is given a special name which is called Hofding's inequality. So this was the final name which was missing. And just as a last thing, what is meant by independent? Independent means probability of x1 and x2 is equal to probability of x1. How is that equivalent to delta? I don't know. When it had to draw a straight line, it wasn't drawing it, and now it is making a delta. Fine. So it is probability of x1 times probability of x2, that is the joint PDF, is equal to product of marginal PDF. And when you do this, then the variance thing holds. So that is it. We have done all the concentration inequalities, and hope you enjoyed it. We will move further with some algorithms, and we'll try to find out their upper bounds very, very soon. Thanks.